Welcome back. In this video we take a look at the create table command. But first, let us discuss the structure of a table. A table is the core component of a relational database, structured as rows, or records. Each row represents a single entry or instance of data. Columns, or fields. Each column represents a specific attribute or property of the data. To store meaningful and structured data, each column must be designed with a specific type of information in mind. This brings us to an important concept: data types. Choosing the right data type ensures that the database enforces rules on what can be stored in each column, helping maintain consistency and accuracy. Data types and their role in data integrity. Every column in a table has a data type, which defines what kind of data can be stored in it. Choosing the right data type ensures data integrity, by preventing invalid entries. If a column is defined as an integer, you cannot insert text into it. And there are more advantages. It reduces storage waste. Choosing the right data type minimizes storage use. Optimizing performance. Indexing and searching are faster when data types are correctly assigned. Common data types for cross-platform compatibility. These data types can be more or less used between database systems. But, do not rely on me, do your own research for cross-platform compatibility. Numeric data types, for storing numbers. Integer, whole numbers. We will discuss integer in more details later in this video. Big integer, larger whole numbers for massive data sets. Small integer, smaller whole numbers. Decimal or numeric, exact decimal values, useful for financial applications. Real, approximate floating point numbers for scientific data. Character data types, for storing text. Character, fixed length string, character, 10, can store up to 10 characters. Variable character, variable length string, variable character, 255, stores up to 255 characters. Text, large text storage, can vary by database. Date and time data types. Date, stores only the date, year, month, day. Time, stores only the time, hour, minute, second. Timestamp, stores both date and time. Boolean data type. Boolean, stores true or false. Some databases use tiny integer, 1. Binary data types. Blob, binary large object, used for storing files, images, or encrypted data. For real cross-platform compatibility, this list would be smaller. So do not forget to do your own research when choosing data types. Many organizations plan for future migrations, whether to reduce costs, like moving from SQL Server to Postgres, to eliminate licensing fees, or to switch to a more scalable solution. Because not all database systems support the same data types, choosing widely supported types can make migrations smoother. If you do not plan to migrate between database systems, you can of course use all available data types for your specific database system. I do not recommend doing that, but it is up to you. Final thoughts: best practices for table design. Use meaningful names for tables and columns, like users instead of table 1. Choose the right data types to balance performance and storage. Index wisely. Too many indexes slow down inserts and updates. Enforce constraints, like primary key, unique, and foreign key, for data integrity. Think about scalability. Will this table still perform well if it grows to millions of rows? Let us explore the create table command, which is fundamental to working with relational databases. The good news is that create table is quite similar across most relational database management systems. Whether you are using MySQL, Postgres, SQL Server, or SQLite, the basic syntax remains almost the same. Let us take a look at a simple example. Imagine we want to create a table to store customer information. In most databases, the command would look like this. Create table. Customers. Opening parenthesis. ID. Integer. Name. Variable character. Opening parenthesis. 100. Closing parenthesis. Closing parenthesis. Semicolon. Here is what is happening. We define a table called customers. We create an ID column, which is an integer. And the name column, a variable character field which can store up to 100 characters. This structure is very similar across databases, with only minor differences in syntax. Now, what if you no longer need a table? That is where the drop table command comes in. The command is straightforward. Drop table customers, semicolon. In most database systems, drop table works exactly the same. It completely removes the table, along with all the data inside it, so be careful when using it. Create table. Let us take a closer look at the general syntax of the create table statement, and some important rules to keep in mind when naming tables. The basic structure of the create table command is as follows. Create table. Table underscore name. Parenthesis. Field name. Type. Parenthesis, semicolon. Here, table underscore name is the name of the table we want to create. It must be unique within the database, meaning no two tables can have the same name in the same database. Now, a few words on what makes a valid table name. Avoid reserved words. Words like select, table, or insert have special meanings in SQL, and cannot be used as table names. In some relational database management systems, you can enclose these table names in quotes, though it is best to avoid them altogether. No special characters. Stick to letters, numbers, and underscores. Some databases may allow other symbols, but it is a good practice to keep names simple and readable. Basically, the same naming rules apply as for create database, as we have seen in the previous lesson. Another important thing to note, not all database systems allow creating an empty table. That is, a table with no columns in it. Some relational database systems require at least one field to be defined. For example, the following command will not work in many databases. Create table. Table underscore name. Parenthesis open and close. Semicolon. Most databases expect at least one column inside the parentheses. If you try to create a table without any columns, you may get an error. Whenever you are defining a new table, always include at least one field to store data. In this section we covered the create table syntax, rules for naming tables, and why you always need at least one field. Does create table work in all database management systems? A common question people ask is, does the create table command work the same across all relational databases? The answer is yes, but with some important differences at the field level. Most relational database management systems follow the same general structure for creating tables. However, the data types you use may vary between systems. For example, let us look at the create table statement we used earlier in this video. While this syntax will work in most databases, there are some key differences to be aware of. Some database management systems offer a broader range of data types than others. For long strings, some databases use text, while others prefer an variable character, max. Boolean support varies, some databases have a dedicated Boolean type, while others use tiny integer, where 1 means true and 0 means false. Certain databases may automatically adjust the specified data type to fit their internal structure. To avoid compatibility issues, it is best to stick to data types that are widely supported across database systems. This ensures a smoother transition if you ever need to migrate to a different database in the future. I keep emphasizing this because I have seen companies spend over a year updating both their database and the applications that rely on it. Meanwhile, they still had to implement new government requirements in the old system, creating extra work and unnecessary costs. To avoid issues, always check the documentation for your specific database to understand which data types are available and how they behave. While you are at it, also verify their compatibility with other database systems to prevent future migration challenges. In this slide, we will walk through creating a database and a table in MySQL and MariaDB, and discuss how table structure is defined. Let us start with creating a new database. In MySQL or MariaDB, you can do this with the following command. Create database persons, semicolon. This command creates a new database named persons. However, simply creating a database does not mean the system automatically knows which database we want to work with, especially if there are multiple databases hosted on the same server. Before we can create tables, or perform any operations inside it, we need to explicitly select the persons database as the active one. This step is crucial because RDBMS systems, like MySQL or Postgres, manage multiple databases under a single instance, and they rely on us to specify which one to use at any given time. For example, in MySQL, we use the command, usePersons, to switch to it, while in Postgres, we might connect to it with \cPersons. Without this selection, the system would not know where to direct our subsequent commands, potentially leading to errors or unintended changes in the wrong database. As mentioned earlier, in MySQL and MariaDB, we do this with the use command. usePersons, semicolon. This tells the database system that all the commands we run from now on should apply to the persons database. Creating a table. Now, we can define a simple table inside this database. Create table. Names. Parenthesis. Name. Variable character. 50, in parenthesis. Age. Integer. Parenthesis. Semicolon. Here is what is happening. We create a table called names. It has a column called name, which stores text up to 50 characters long using the variable character, 50, data type. The age column stores whole numbers using the integer data type. By the way, in MySQL and most databases, int and integer are the same, so you can use either one. I think there is one database system that does not support integer, so it is wise to stick to int. Understanding table structure. The list inside the first and last parenthesis is called the column definition list or table schema. This schema tells the database how the table should be structured, including column names, like name and age. Data types, like variable character 50 and integer. Any rules or constraints on how data should be stored. By defining a clear table schema, we help the database store and retrieve information efficiently. We have created a database, selected it for use, and built a table in it with defined columns. Let us take a closer look at variable character 50 and what it means when defining this column in a database table. When we use variable character 50, we are telling the database that this column can store up to 50 characters. But, unlike a fixed length data type, variable character only uses the space it needs, plus a few extra bytes to store the actual length of the text. For example, if you store the word, John, in a variable character 50 column, it will not take up all 50 characters, just 4 characters, plus some additional storage for tracking the length. Variable character has some great benefits, especially when working with variable length text. Space efficiency, it only stores what is needed, reducing wasted space. It uses less storage space. Compared to fixed length types like character 50, variable character saves space when storing short values. Improved performance. Smaller rows mean more rows can fit into a single database page, which can speed up queries. Saying that, variable character is not always the best choice. There are some downsides. Less efficient indexing. Indexing variable character columns is generally slower compared to fixed-length data types like character. There is storage overhead. Since variable character stores extra bytes to track the length of each value, there is some additional storage cost. Fragmentation. Over time, if data is frequently updated or changed, it can lead to fragmentation, and this reduces performance. Choosing the right length. One common mistake is always using variable character 250 for everything. While it might seem like a flexible approach, it can lead to wasted space and performance issues. For example, an email address column is a great use case for variable character, but you do not need 250 characters. Most email addresses fit within 100 characters, so variable character 100 is a more efficient choice. Choosing the right variable character length helps balance storage efficiency and performance. In this lesson, we will explore the integer data type, a fundamental type used to store numbers in databases. The integer data type is used to store whole numbers, and it always takes up 4 bytes of storage, regardless of the value. This fixed size has both advantages and disadvantages, so let us break them down. One of the key advantages of using integer is its predictability. Since integer always uses 4 bytes, the storage space is fixed, and you can be sure of how much space it will take. Arithmetic operations like addition, subtraction, multiplication, and division are very fast with integer, making it ideal for calculations. Indexing is also quick because of the fixed size, which allows for efficient searching and retrieval of data. Another benefit is no confusion. Since integer only stores whole numbers, there is no need to worry about decimal points or rounding. Now, let us talk about the range of values that integer can store. For signed 32-bit integers, the range is from -2,147,483,648 to 2,147,483,647. This range is more than enough for many use cases, like storing user IDs, counts, or age. However, there are a few disadvantages to consider. Fixed size. Since integer always uses 4 bytes, it is not the most space-efficient solution for very small numbers. For example, if you only need to store values between 1 and 100, using integer still takes up 4 bytes, which is more than necessary. Only whole numbers. Integer only stores whole numbers. If you need to store decimals, you will have to use a different data type, like float or decimal. Unsigned integer. There is an alternative called unsigned integer, which eliminates the negative values. By removing the negative side of the range, the values are shifted upwards. With an unsigned integer, the range expands from 0 to 4,294,967,295, giving you a larger positive range. This is useful if you only need to store positive numbers and want to maximize the available range. How does the database know which one to use? Well, you have to define it yourself. In MySQL, you can explicitly declare an integer as integer, unsigned, if you only need positive values, which increases the maximum range. Postgres and SQL Server do not support unsigned integers, so if you need a larger positive range, you must use big integer. By default, if you do not specify anything, most databases assume a signed integer. Conclusion. The integer data type is a great choice for storing whole numbers, and its fixed size and fast operations make it perfect for many applications. However, if you do not need negative numbers, consider using unsigned integer to expand the range. Let us go back to variable character. When I have to import data from a CSV file, I always use variable character 100 or even 250. The reason is that it is not always easy to see what data you receive. Once the data is in a table, it is easier to see how long the fields have to be. For fixed-length field files, that problem does not exist, but you may have to count out each field if there is no data dictionary. If you do not know the exact field lengths in advance, using variable character 100 or 250 as a temporary solution is practical. It ensures that all the data gets imported without truncation issues, giving you flexibility to analyze the actual field lengths later. Pros of this approach: prevents data loss. If you set a column too short, you risk truncating valuable data. Using a longer variable character prevents that. Flexibility. Once the data is in the database, you can analyze it with the length function and optimize field sizes accordingly. It avoids import errors. Some databases might reject rows if a string is too long for a column, so using a larger variable character avoids that initial headache. Downsides: yes, there are. Storage overhead. If left unoptimized, using large variable character fields can waste space, especially if the actual data is much shorter. Indexing performance. Indexing on long variable character fields can be less efficient than indexing on shorter, fixed-length fields. Lack of constraints. If a field is always meant to be, say, 20 characters, keeping it at variable character 250 long-term might allow unintended data. Best practice after import. Once the data is in, you can run queries like select max, length, column_name, from table_name, to determine the actual longest value in a column. Then, you can adjust your schema accordingly, using alter table to shorten column lengths as needed. For fixed length files, if there is no field description or specification, manually counting is necessary, which can be tedious. But at least once you have set the lengths, they are predictable. Here is how to use max length in MySQL. Select max length name from the names table. In my case it will return 5, the names are Alice, Bob, Carol. There is also a select minimum length. Select min length city from the names table. It returns 7, the cities are New York, Los Angeles, Chicago. For Postgres you should use character_length, and not length. For SQL Server, length is too long, only use the first 3 letters, len. Some unique data types may cause portability issues if you switch databases. My advice: do not use them, unless you really have to. Here are the data types I try to avoid. JSON, enum, unique identifier, tiny integer, 1, set, year, 4, geometry, point, polygon, serial, and big serial, array, hstore, UUID, date time offset, money, and small money, hierarchy ID, XML, stored, and virtual. How to avoid portability issues. Stick to common SQL types: integer, decimal, character, variable character, boolean, text, date, and timestamp. Avoid database-specific features unless necessary. If using unique types, add comments in your schema for future migrations. Test queries in multiple databases before deployment. Normalization and denormalization. Normalization, breaking data into multiple related tables. This prevents redundancy but can slow down complex queries. Denormalization, storing redundant data for quick access. This improves read performance but increases storage usage. Database design. Normalization is the process of organizing data to minimize redundancy and improve data integrity. This is done by structuring the database into multiple related tables, reducing duplicate information. The main benefits include efficient storage, easier updates, and avoiding inconsistencies. For example, Storing customer details in a separate table and referencing them via a unique ID prevents unnecessary repetition across orders. However, normalization comes with trade-offs. Highly normalized databases require frequent joins to fetch related data, which can slow down performance, especially in read-heavy applications. This is where denormalization becomes useful. Denormalization involves intentionally duplicating some data or storing pre-computed values to speed up queries. A common example is keeping a total order amount column instead of calculating it dynamically from line items every time a report is generated. The choice between normalization and denormalization depends on the use case. Transactional databases, OLTP, typically favor normalization for data integrity. Analytics-focused databases, OLAP, often use denormalization for fast querying. The best approach is to balance both techniques based on performance needs and data consistency requirements. That wraps up this video on creating tables. In the next video, we will dive into creating tables, the theory. I look forward to seeing you there.